Hello, everyone. This video is going to be about topic 1.1, introducing calculus. Change can occur at an instant. Okay, so these are the notes that we're going to use. There'll be some problems where you might want to pause it to try to do them yourself. I'll try to indicate that, but feel free to, if you need more time, slow the video down, and be sure to ask questions on my Google Classroom. Okay. So the concept of rate of change, all right, and we're going to focus that on mostly nonlinear functions. You've all seen rate of change before in algebra 2. Rate of change is otherwise known as slope of a graph, but we're going to talk about average rate of change. So in real world context, it's the change in a quantity divided by an elapsed time. But we don't always talk about time. So for a function, for any function, we refer to this change as the change in the output value divided by the change in the input value for any two distinct points on a graph or of a function for that matter. Linear functions, if you find any 2 points, have a constant rate of change, meaning that the average rate of change is the same between any 2 points of the graph. This is often referred to as its slope, like I said before. Okay, so you guys have seen this formula before. In the early days, you might have seen y2 minus y1 all over x2 minus x1. You might, in your science classes, might have seen it as the change in y over the change in x. Ultimately, these are just different variations of the same formula. Okay, so I have a graph here, so for f of x, and what I want to do is I want to find the average rate of change between over the following interval. Okay, so if you know how to do average rate of change using the formula, feel free to pause it. I'm going to do it along with you so you can see the answers, and we'll kind of go from there. So I want the average rate of change between -3 and 1, between the x values of -3 and 1. So at -3, I'm here. At 1, I'm here. I'm going to draw a little secant line between those 2 points, okay? And I want that slope. Now, you could probably get the rate of change of that secant line just visually looking at it, but I'm going to do it algebraically just so you can see the calculation. So at -3, the y value is a -2. At 1, the y value is a +2. So now if I find that average rate of change, I'm going to say 2 minus -2 all over 1 minus a -3. And if I do that calculation, I get 4 over 4, which just gives me an average rate of change of 1. Okay. So if I go to the next interval the same way, I want the average rate of change from -5 to -1. So at -5, we're all the way on the left side of my graph, all the way to -1. Okay, making sure you're on the curve. Again, I'm going to kind of make my secant line here. Excuse my stylus. Let's get my stylus going. There we go. Okay. So you can probably visually look at that and you can tell me that the average rate of change is going to be 0. But again, I'm going to prove it algebraically. So at -5, we're at the y value of 2. At -1, we're also at the y value of 2. So if I did that change of y, 2 minus 2 over the change in x, -1 minus a -5, I get 0 over 4, which is an average rate of change of 0. Okay, and then last but not least, part C is just a different way to write an interval. So we have interval notation here instead of the inequality. But if I do the average rate of change between 0 and 1, let's get that going, between, there we go, 0 and 1. Again, you can see that secant. I'm going to write my coordinates. So at 0, I'm at a y value of 4. And then at 1, I'm at a y value of 2. So 2 minus 4 all over 1 minus 0 gives me a -2 over 1, or just an average rate of change of -2. Okay, so that is ultimately how we calculate an average rate of change. For example 2, rather than giving you a graph, I just give you a function g of x. So we're going to do the same kind of idea. The only difference is I'm going to use my calculator, okay? And I want to show just some basic features of the calculator. I kind of put a little box here. So I'm going to pull up my TI-84. And in my y equals menu, I'm going to type that function in. So x squared minus 3x minus 10. Okay, and if you go into the table set, so second and then the window button, what we can do is we can change the independent to ask. And now a lot of my students freak out because then when you go to your table of values, it's blank. But ultimately, what we can do to kind of speed things along is I can take, excuse me, I got my toolbar's in the way. I'm going to take my -8 and I'm going to press enter, and I'm going to take my 1 and press enter, and it gives me the output values for those two inputs. So I know my points that I'm going to be working with, excuse me here, are -8, 78. So -8, 78. And then the other one was a 1, -12. So if I find that average rate of change now, so -12 minus 78 all over 1 minus a -8, and that gives me a -90 all over 9, or in this case, a -10. So my average rate of change of that function is a -10. Okay, and I could do the same thing again. Feel free to pause. You could do it on your own. I'm just going to type in the next two y values, 0 and 9. And I know 0 is -10 and 9 ended up being, I believe it was 44. Yep, there we go, 44. So if I find that average rate of change, I'm going to have 44. Oop, let's get that stylus working. Okay, minus -10 all over 9. Ugh, struggling. Let's see if I can get my tip. All right, 9 minus 0, which gives me 54 over 9, or in this case, 6. Okay, so those are my two average rate of change. Now, I do want to show you one other cool thing in the calculator. Your calculator doesn't really have to be in a fancy setting. Any new TI-84 can do this. If you hit the alpha button and then y equals, a little menu pops up. So it's really the F1 menu. If you turn on the fraction thing, okay, so you can see the lights blinking. I'm going to hit alpha F4, y1 of 9, because that's the second input value, minus alpha F4 of 0. And then on the bottom, I'm just going to say 9 minus 0. And if I do that, it will calculate the average rate of change for you, right? So it's pulling the function that you put into y1 and using that to calculate the average rate of change. So if you put the function into your y equals menu, you can do calculations very, very quickly. All right? So hopefully that helps you in the future. All right. So we're going to scroll down. So we're going to do the same thing. We're going to find the average rate of change from a table of values. So in this case, if you want to pause it, you can find the average rate of change and just check your answers along the way. I'm going to change the color of my pen here just to make something different. So at 26, I know I have the y value of 18. And at 20, I have the y value of 5. Now I kind of flip-flop my numbers here, but ultimately you should get the same answer regardless. So if I did 18 minus 5 all over 26 minus 20, I get 13 over 6, which does not really reduce. So I just get the average rate of change of 13 over 6. Okay. Now in part B, I kind of made a little typo here. I got to fix that on my original document, but it's kind of a true or false question. The average rate of change on any closed interval for f of t, and I want to put is the same as the interval from 20 to 30, right? So will there be any interval between 20 and 30 that's going to have the same average rate of change? And we're going to kind of talk about that reasoning. And this is actually going to build up to a theorem we're going to talk later on in the class. So I want to find that average rate of change, excuse me there, from 20 to 30. So I'm going to go from 45 minus 5 all over 30 minus 20. And if I do that, all right, if I do that, I get 40 over 10, which is just the value of 4. Okay. So now, is there going to be any average rate of change between any two values of my table that will also give me the value of 4? So you have to kind of look through your table of values to see, you can do these calculations in your head pretty fast. If you use any of those t values, 20 to 22 won't work. 20 to 24 won't work. Again, as far as explaining your reasoning, you can show all those mathematically. Again, this for part B, for this particular early in the year, this is just meant as more of a thought-provoking than a writing. But if I really wanted to show it, I could show all the intervals that won't be the same. And in this case, I don't think, if you check them all, I don't think there are any values that are the same. So I would say that this is false. Okay, there are not going to be any values that are going to be the same as 20 to 30 from the table of information given. Okay, now example 4, we talk about more of a verbal approach. Okay, so I don't want to know necessarily what the value is, but instead I want to know what the units of measure will be. So can you explain the meaning using correct units for the average rate of change in each context? So for part A, for t greater than or equal to 0, hours h, oops, let's get rid of that. And this should probably be an h of t. So I'll fix that in my notes as well. But h of t is a differentiable function of t that gives the temperature in degrees Fahrenheit of a house in Houston in July, where t is measured in hours since midnight. Now, if I do the change in output over the change in input, okay, I'm going to take the unit of output, which is degrees Fahrenheit, and I'm going to divide that by the unit of the input. So the change in the input would be hours. So my average rate of change would be the degrees Fahrenheit per hour. Okay, that's what I'm looking for. So for each of these, I'm looking for what the unit of measure is. Okay, now again, you can pause and you can try to do the next two on your own and check your work if you like. So I have a water main that's broken, and a flow meter gives the rate R of t at which water is gushing out of the pipe in gallons per minute. So my output of this function is going to be gallons per minute. Let's see if I can get my pen back working. Okay. Been a little fidgety today, so bear with me. Luckily, you guys got the fast forward. You can just go ahead. There we go. Okay. So the output is gallons per minute. Okay. And I need to still divide that by the unit of the input. So if the output is gallons per minute and the input is in minutes, a better way to write that is gallons per minute squared. Okay, that would be my unit. So part C, the cost C in dollars per mile. So the output is in dollars per mile of digging a tunnel through a mountain varies with the distance x. So x is my input, and it's a measure of distance in miles. So I have to do it over the change of x, which is miles, and I get something like dollars per mile squared. Okay, so that's ultimately what my unit of measure would be. Okay, so I have a little discovery activity. This is going to kind of lead into where this class is going with average rate of change. What I want you to do is I want you to plot each set of points that's given for the interval. Okay, I want you to use a ruler to draw the secant line. All right. And then I want you to calculate the average rate of change for each of the intervals, okay? And then you're going to kind of see a pattern. After you do that, I want you to try and answer the questions below. So what I want you to do is I want you to pause. I want you to complete this discovery activity, okay? So again, we're going to plot each of these, all right? And then we're going to find the average rate of change. And then what conclusions can you draw, right? And then, you know, what can we talk about a secant line for the graph provided? So from 1 to 3, all right, so I did these calculations already. So just to speed the process up, from 1 to 3, my average rate of change was 2. From 1 to 2, my average rate of change is 1, 1/2, 0.1, or you might have written it as a fraction, 1/10. 0.01, 0.001, and let's go 0.0. There we go. Okay. Now, if you look at the secant lines, if I go from 1 to 3, we start up here, you know, I have this secant line, okay? And then I can go from 1 to 2. 2's right here, so. And then from 1 to 1.5. And then after that, it gets pretty hard to draw if you're drawing it. So from 1 to 1.1, and if I keep going here, you can kind of see a pattern with these secant lines. All right. And I think there's one more. We'll use orange. You know what? We're going to use pink. All right, so I have these secant lines here between the points. So what conclusions can we draw from completing the table of values? Well, as the points, right, so I'm going to go back to a normal color here. So as the second coordinate gets closer to the first, it seems the average rate of change is getting closer to 0. Okay, so if you look at the table, we started at an average rate of 2, but as those points kind of get closer and closer together at the value of 1, you know, our average rate of change is getting smaller. It's getting, you know, 10th, 100th, 1000th 10,000th. So it's getting very, very small. What conclusions can you draw from constructing the secant lines? I can probably say that the closer that those 2 points get together, so I'm going to say the closer I'm going to say the second coordinate gets to 1, the more horizontal the secant line will be. Okay, and ultimately, if I ever could get to 1, it probably would be horizontal, right? So if I put 2 points on top of each other, that would probably give me a horizontal line. And that's probably only because it's at the vertex there, but you know, kind of keep going. So this is the last piece for topic 1.1. It's the same graph, okay? So we're going to talk about something called instantaneous rate of change rather than average rate of change. So the rate of change at a particular moment is an instantaneous. So it's at 1 point instead of 2, being that it's instantaneous. So same as the value of the derivative at a particular point. So you're going to see this word a lot in the coming topics. That's the derivative calculates an instantaneous rate of change. So for a function, the instantaneous rate of change at a point is the same as the slope of the tangent line, not the secant. Okay, the slope of the tangent line defines what that slope is of the curve at that instant. Okay, so using what we've learned to approximate the value of instantaneous rate of change, approximate the value of the instantaneous rate of change when x is 2. So I want to know, what is the instantaneous rate of change going to be when x is 2? So ultimately, what I want to do is I just want to calculate the instantaneous rate of change between 2 and 2.01. I want to calculate the instantaneous rate of change between 2 and 2.001, right? So on and so forth. So if I do this and I get progressively close, it's going to start to give me an idea of what that rate of change is getting closer and closer to. Now, I strongly recommend you do a few points. You don't just do one, okay? Don't just start at the end. Now, don't get me wrong. You can start with the last one, but do a couple more after that, just to make sure it's getting closer and closer to a value. So I kind of did these average rate of change already. I would pause. I would use your calculator. You know, I would do the same feature that we did before. So if I use my calculator in Y1, you know, we have a different function here. I have x squared minus 2x. And if I then change my my average rate of change formula to use those values. So I'm going to go from not 9 to 0, because that was the first problem we did. We're going to go from 2 to 2.001. And then I'm going to go from 2 minus 2.001. And if I calculate that, you know, I get an average rate of change of 2.001. Now that's coincidence. It won't always be the second value. But if I do the next one, I did this already. One, and if you did another one, it gets even closer. So what can we conclude, right? I'm going to say that the instantaneous rate of change at x equals 2 is 2, right? It's going to get closer and closer to the value 2. Now, your justification is showing the work. If you show the work showing that it gets progressively closer, getting closer to 2, that is enough to justify your answer mathematically, okay? And that's very, very important, okay? So now, identify all the x values at which f of x has a negative instantaneous rate of change. So ultimately, I want to look at this graph and I want to know, where is this graph going to have negative slopes? And if you look, this graph is decreasing on the entire left side all the way until the x value of 1. So what we're going to do here is I'm going to say from negative infinity all the way to 1. Now, not inclusive, because at 1, we talked about earlier on the earlier example, that was actually a 0 slope. That wouldn't be a negative slope. So I don't want to include the 1. However, on the right side, we know all the instantaneous rate of change are positive. Now I copied and pasted, so you can see a little typo here. I want to know for this last part, where are these positive? And that's going to be from 1. Oops. Well, we can do interval notation, or you can do inequality notation. Just make sure you don't include the 1 there because I don't need that parentheses. Because ultimately the slope at that point is not positive nor negative. Okay. So that kind of concludes the notes for topic 1.1. If you look, we found average rate of change from a graph. We found average rate of change from a table. We found the average rate of change in terms of a verbal expression. So different, I'm trying to give you different looks at this topic. And then we did that little discovery activity trying to get to this concept of an instantaneous rate of change. And that's the slope at 1 point. It's when I get closer and closer to a specific value. Okay. So hopefully this helped and you can complete any preceding tasks.